is when gamma is 0.75. Okay? So if your actual gamma turns out between the two, what you do is an interpolation. Okay? You just approximate. Now, the way these figures work is that on the horizontal axis, you're plotting the moment divided by AG times H, where AG is the cross-sectional area of the column, H is the height of the column, the depth. Okay? On the vertical axis, you got P divided by AG. Now, say I tell you, all right, you got a column, and on this column, there's an axial force of 1,000 kips, and there's a bending moment of 1,200 kip feet. Okay? So we know the moments. We know this moment here, and we know P. Now, the next step that you would do is you would assume a section of concrete. So, in other words, assume a concrete AG and H. Alright, so now you know the vertical axis and the horizontal axis. Okay? So say I picked a section that gave me a point right here. Okay? I picked the cross-sectional area and its depth H on this axis, and the same AG on this axis cross-sected at this point. Okay? Is everybody with that?
So those are both just assumptions. We don't know if they're right or not.
Those are assumptions. So in other words, for 1,000 kip, all right, let's see here. So let's assume that this number here is 1.5 vertically. Okay? What I'm going to do is, if P is 1,000, I'm going to make this thing
Well, I don't know now that you mention it.
1.5, I guess it's going to be about 667.
Make it 1.4 because that's where you put the space.
All right, 1.4.
All right, so you want
So P is 1,400.
P sub n is equal to 1,000?
Let's call P sub n is equal to 1,400.
1,400.
All right?
Is that with the fee or not?
That's with the fee.
Okay. And you
So your demand is 1,400.
All right, and you want it divided by the area gross. You want that to come out 1.4.
All right. So what I'm saying is AG is equal to 1,000.
Just 1,000. You're right. So
Okay, that gives me 1.4.
That's 1,000 square inches column you've assumed.
All right. Now, I also plug that AG onto the horizontal axis with H. If I assume it's square or rectangle, I have to assume an H. So I can come up with the horizontal axis. And then this intersects at this point.
Okay.
Okay, so now I picked out a shape. And this thing here, if it's square, take the root of 1,000.
31.6.
So this is 31.6 by 31.6. Okay, that's the size of my column that I'm going to assume. Now, based on that column, this point intersects right here. Now, what you see here are interaction diagrams based on various amounts of steel. And if you look, this is rho G. 1%, 2%, 3, 4, 5, 6, 7, and then the last one is 8. This star falls in between the 3 and the 4% reinforcement ratio. So this looks like it's about 0.35. Okay? So if you take 0.35 times 1,000, what this is going to give you is 3.5?
0.035, enter 1,000 times
35.
35 square inches of steel.
You need 35 inches square of steel for this particular column. Now, obviously, those numbers are way off, but that's how you would use this table.
So you're saying, in other words, and that's it. That tells you everything's okay, as long as you cram 35 square inches of steel in the column.
Right. So what you did was you selected the size of your column that was 31 by 31, and then you came up to this point and it told you how much steel to use.
And
okay, now that's based on this gamma. Okay?
So that's just based on putting them at that distance.
Right.
So you're saying now then if that 35 square inches of steel comes out more than 8%, I need to go pick up bigger...
You need to pick up a bigger size then, right.
Bigger chunk of concrete.
You try and keep your star so that it forms in this region.
Where?
Down in this lower part.
Oh, it's got to work, doesn't it? Because the row was under 8%.
That's correct. The worst one is 8%.
Yeah, if you didn't go out in here in the first place, you know it's okay.
Right.
Okay.
Like I said, the only way they really can do a problem like that is if you have these charts. So if you see a column with... Yes, sir.
Yeah, just take...
Well, for this diagram, you'd have to put half the bars in.
Take 35 square inches and divide by 2, put on both sides. And then go find some reasonable number of bars that gives you half a 35.
Yeah, I selected a P that was too high. All right, but let's say this number's turned out to be 4 inches squared. All right, let's say my P was selected properly, and the area of steel that was required was 4 inches squared. Now I know that the area of a number 9 bar is 1 inch squared. Okay? So if my number 9 bar has a 1 inch square area, I know I need 4 of those. So what you would do in this, 1 in each corner. That's correct. So you put half the bars on one side, half the bars on the other, and space them out in the corners as best as possible. Now if it turned out that I needed 6 inches squared, I put 3 on one side, 3 on another. Okay? Now this is with steel only on 2 sides, so it's really bending only about this. It's only bending about this axis. Okay? Remember, your steel goes into tension.
And the right side goes into compression.
Now there's other ones when the steel is more uniformly distributed around the column. All right, and I think that's on your 3rd and 4th sheets. Okay, so if you want to place steel all the way around the column, so this has bending in both directions, you would do it something like this. All right, use these flow charts and space the steel uniformly around your column.
And that's actually for bending just about the one axis shown, but you pick up some more strength because of the other bars.
So,
Okay.
right. Does everybody sort of get the hang of those? You may have had something like this when you're taking your concrete class. This was these were design aid tools before computers. Now that we have computers, these computer programs spit these interaction diagrams out in a matter of a couple of seconds. Okay, so these are very old charts, but you know they work for an exam like this. We talked briefly about lap splices, and if you're in a compression zone, if your column's only in compression and you're up here on the interaction diagram, then it's a compression lap splice. If it falls between a stress in the steel of 0 and 0.5 of Fy, you're using a Class A tension splice.
Are those numbers, are those little lines marked on those graphs?
I'll show that in a second.
Okay.
All right. So if you're between 0 and 0.5 Fy, you're using a Class A, and if you're beyond the 0.5, you're using a Class B. Now the way you can tell where you're at on these interaction diagrams is look at the lines going radially out from the origin. Take a look right here. Right here, you see you got an Fs is equal to 0.5 times Fy. Alright? So if your point falls up in here, then you design it as a compression lap splice. The Fs equal to Fy is this line right here. Okay, do you guys see that on your charts? Okay, so those are your lap splices. Now, in your column, you also have to have, well, they serve 2 parts, these ties and stirrups. Okay, number 1 is that they can be used for shear, and number 2 is if they're not there, what's going to keep those column bars that are vertical from buckling out? Those things are very flexible. So you need some ties to keep them together, and those are called anti-buckling ties. And you use number 3 ties for number 10 bars and smaller, and number 4 ties for number 11 bars and smaller. Now, I don't know if you guys remember, I always bring this up in my concrete class, but the Loma Prieta earthquake in San Francisco, you remember those double-decker bridges? Well, what happened is at the joint, all right, where you have one deck, your second deck, and then these columns connected to decks. Well, they had ties at these columns that were insufficient. And what happened was those ties busted, and those columns actually buckled out, and you had shear failure that occurred at that joint. So that created the top slab to drop down onto the bottom one. Okay, so these bars sort of serve some of that purpose, all right, is to prevent buckling. And the requirements from the code is that the maximum spacing must be less than 16 times the diameter of the longitudinal bar, must be less than 48 times the diameter of the tie, and also less than B and H. Okay, those are minimum requirements. Tie arrangements, if you have a 4-bar column, is pretty much going to be a stirrup that goes all the way around. If you have 6-bar column, it goes all the way around, and there could also be an additional one in the middle, possibly, if you need it. If you have 8 bars, you could have a bar on the outside of all these, plus the diamond shit. Okay? 10-bar column could look something like this, and a 12-bar column could do something like this. All right, think about confinement. How are these guys being held together? How's the inside core? Well, obviously this last one looks to be pretty much the best, right? Take a look on this inside here, and think about that concrete, how it's going to explode. Really, it's hard to explode because these stirrups are all holding it together. Whereas over here, it's not as good. Okay? What are you showing?
B equals what? H equals what?
Okay. B and H from this expression above. S max must be less or equal to B and H. B is the width of the column, H is the height of the column. Okay, so those are properties of the cross-section. Now, ties also serve another purpose, the shear reinforcement. Now, if the demand turns out to be greater than 1/2 phi times the resistance in the concrete, then you need to provide shear rebars, okay, or stirrups, just like we did in beams. And the spacing must be less or equal to D over 2. Now, there's also special requirements for lap splices. So when you have to overlap these bars, you have to provide additional ties to make sure that that splice performs well under earthquake-type loads, etc. And those are in these sections of the code. I just identified those for you now. On an exam, God, I hope to God they wouldn't ask you something like this. If you're designing a spiral, you have this formula from the code. It's in equation 10.5. The spacing of the spiral must be less or equal to pi times the diameter of the spiral squared times Fy divided by 0.45. D sub C is the diameter of the core concrete. So in other words, the concrete that's inside the spiral. Fc prime, we know Ag is the cross-sectional area of the column. A sub C is the area of the core. Again, it's the area of the concrete inside the stirrup. And if I show you that, these are my bars. This is my stirrup. So the diameter of the column is the outside diameter, and I guess that's not even required. That would be D.
Yeah, you'd use that for area gross, wouldn't you?
This would be D sub C, right? The area of the core would be this much, and then the area gross is the pi D squared over 4.
You get to go to the outside of the surface of the spiral for area.
That's correct.
Okay.
Okay, does everybody catch that? Now, when you calculate your S here, it must also be less than 3 inches, and that's for proper confinement. To avoid congestion, it must be greater than 1 inch. Alright, now you're going to get in this high seismic zone, spirals are used quite a bit, and these things could be spaced at 1 inch spacing. So just imagine having a column that's 12 feet tall with number 10 longitudinal bars, and then you have these hoops at 1 inch spacing. Alright, all the way up this column. Just imagine trying to pour that concrete. Alright, it's difficult, but it's required to resist the earthquake.
Is that spacing, again, clear space, or is that space between the center line of the bars?
This spacing S is the center line distance of these bars. Okay? Now, also in a column, what happens if it's a very slender column? Then there could also be buckling problems. Now, I'm not going to get into that, and I doubt if the exam will, but there's a specification in the code, it's in 10.11, that says that the design moment is some amplification factor times the moment M2B times another amplification factor times M2S, where these deltas are defined in these two equations, and it's basically a function of buckling. Alright, the B refers to braced, the S refers to side sway. So you have moments due to braced action, like gravity loads, and then moments due to side sway loads, which are earthquakes and wind. Alright, that push it laterally. If KL over R, alright, where L is the length of the column, the height of the column, R is the radius of gyration, and K is the effective length factor. If K over R is less than 34 minus 12 times 1 M1B divided by M2B, this is the ratio between the moments in the top and bottom parts of the column, then you can neglect slenderness. If you're in a slender column where it's in an unbraced frame, if K over R is less than 22, you can forget about slenderness. Now again, this is a 2-week presentation in my concrete class that I just showed you on 4 lines. Okay? I'm hoping and praying that they would never give you something like this on a test. Okay? Alright, so as far as realistic problems go, number 1, up to what we cover now, is an easy beam. So an easy beam means like a cantilever, or it's some type of simply supported beam with some loads on it. You can find the shear and moment diagrams, and those are your demands. And then they can ask you to design the beam. Select the B and the H and the area of steel so that you satisfy flexural requirements. And then they can say design the stirrups to satisfy the shear requirements. And then they can say, is this beam going to crack, and if it does, will it be within the allowable cracking of the code, and that's that Z formula. And then you can also check deflections. Now that's a fairly realistic problem for the exam. It's a lot of calculations, but if you go back and take a look at all those flow charts, hopefully it'll get you through it. Columns are so-so. I don't know. They could ask it to you, but you know, again, you're sort of forcing yourself to use those design charts, and I think they're pushing it if they ask you something like that. But you know, I wouldn't hold it against them. I think they probably could do something like that if they wanted.
I think those design charts really make that easy. I mean, you just pick that column off there in a hurry.
Right. So maybe it's worth to take a look at a couple of example problems. Now, the other thing that I know I had on mine, and pretty much every old exam that you look at, and all these example problems, it's something related to footings. Footings is a nice problem on an exam because it's an easy calculation problem. It doesn't require a spreadsheet. All right. So now I'm going to get into footings, and again, this is probably one that very legitimately could be on the exam. Okay. Now I know Dr. Lowry talked to you before about soil pressures, and if you have some spread footing.
Yeah, we didn't associate it with a footing. We just associate it with P over A type of stresses and bending stresses, and if the two are added together, then we didn't call it, due to soil.
Okay, so let me just go through it real quick. Forget the moment for now. If you got a column and it's pressing down on this footing, it's going to create a uniform distribution underneath. Okay? Now what happens if you try and rotate this column? So in other words, you try and twist it according to this bending moment. Well, obviously on the right side, you're going to try and dig it into the soil more, and on the left side, you're going to try and lift it up. When you add these two cases together, what you can get is something like this. All right? Now this is the soil pressure. If we talk about gross soil pressure, normally that considers the weight of the footing, any overburdened soil, and any factored loading. All right, so in other words, the loading from the column, both P and M, are considered. This is the gross soil pressure. So if your soil can only take a certain amount of stress, that's what you're calculating here. You have to make sure that this is less than the allowable.
You might mention, too, that if the stress distribution ever really looked like that in soil, they're probably going to ask you, is it acceptable? Soil can't come up with any tensile stress.
Right.
So if the side really ever did come up with a tension stress, that wouldn't be acceptable because this little piece can't be developed.
Did everybody catch that? Well, I'm losing my voice. You guys got to realize, the most I've ever taught for was 1 hour and 15 minutes.
New record.
I'm dying out quick. Okay, net soil pressure is something a little different. What we do is we neglect any soil above. A lot of times in like bridge type structures where you have this footing, what they do is they put soil on top of the footing itself. And what that does is tries to help settle the retaining wall or the cantilever or the what's that called? I can't remember now. Retaining wall. That's the word I was looking for. Okay. Let's talk about design. First of all, we're going to talk about flexion. It's just bending. How is it bending? It's just like a beam. Same exact thing. There's a critical section, and the best way to think of the footing, alright, if everybody takes a look up at the screen, this footing sits on soil. Alright, what happens if I flip this guy upside down? How do I design this footing for these types of stresses? It's just a beam, right? This guy is cantilever. It's cantilever off the end. Forget the moment for now. If you just had an axial force P, this creates a uniform load. You have a uniform load sitting on a beam that's cantilever. The guy's going to deflect like this. That's how we design for flexion. And this is the critical strength right here, the critical section. Okay? So I'll show you a sheet of that in a second. Now, talking about the critical section, if you have a square or rectangular column, the critical section's at the face of the column. All right, and if you just took a look at the way I drew that deflected shape, that would be the part for the critical moment, just like in a cantilever. It's at the end of the wall. If you have a circular column or some type of polygon, the critical section's at the face of an imaginary square of same area as the circular column. So you have a circular column, it's pi d squared over 4. What you do is you assume you set that equal to some length of column squared. So you can find that length. Alright? And then figure out where that critical dimension now crosses. Alright? Now, I guess the best way to do that is something like this. If I had this circular column, this thing has a certain area. Well, this could be represented by a square column of that area. Okay, and if my footing's over here, what I'm saying is that the critical distance is at this point. Not at the end of the circle, but at the end of this imaginary square. Okay, that's all we're saying there. Now, if you have a footing that's supporting a masonry wall, the critical section's halfway between the middle and the edge of the wall. If you have a column with steel base plates, the critical section is halfway between the column face and the edge of the base plate. Alright? 15.43 says that the flexural reinforcement shall be distributed uniformly across the entire width of a square footing. Okay? Basically, you space the steel out at even spacing. If you're in a rectangular footing, it's a little more complicated. Remember, axial force coming down on this column, the critical sections are going to be along the sides of the column. Okay? And you can see here that the demand moments over here are probably going to be greater. They'll be greater bending in one direction, say this direction, than they would about bending in this direction. Okay? Now, think about bending about AA. Okay? The columns here. What about the stresses out in this zone? They're probably not going to feel too much because it's way away from the column. But since these guys are closer in the other direction when you consider bending about BB, alright, there has to be more uniform spacing in that direction. So there's a certain section, 15.4.4 of the code, for rectangular columns. I'd have to say, well, I can't, they'll probably give you a square column if anything, but if you have flexural reinforcement, go to 15.4.4. Alright, it'll describe it a little more clearly. Okay, the uniform spacing in this problem, alright, let's read it. For rebar, long direction shall be distributed uniformly across the width. Okay, so for example, alright, I read this wrong. For rectangular columns, rebar for long direction shall be distributed uniformly across the width.
That's what you did here.
Okay, so that's
uniform,
1, 2, 3, 4, 5.
Uniform.
Right. Okay, and then a portion of the rebar for the short direction is uniformly distributed in the center, and the rest goes to the end. So these guys here are sort of closer together, and then at the end they sort of separate. Okay. For minimum flexural steel, it's really not specified in the code, but we recommend to use the part from slabs, which is 002 times BH and 0018 BH for the different values of FY. Rebar spacing, the max that you can use is 3 times the height of the footing, or 18 inches. As far as development length goes, again, we must develop at least one full development length, LD, from the critical section. Remember, the critical sections are along this column, so these bars must extend at least LD beyond those in all directions. Okay, so here's flexure. You got your axial load. Forget the moment for now. You got your axial load. This creates a uniform loading underneath. Alright, if you don't like looking at it this way, grab your sheet and do this to it. Flip it over. Okay? And this is what we get. For a moment, the critical section occurs at the column face. So what is the moment? It's the uniform loading times this length times the width in and out times its moment arm. The moment arm, the force is concentrated at a distance of half of this, right? So let's take a look if I flip it back this way now. The moment about axis AA is the uniform loading Q, which I find to be equal to P divided by the area of the footing, which I say is AB. Okay, that's the uniform loading, times B, that's this length, times F, which is this length, times its distance from the face of the column to the centroid of this area, okay, which is at a distance of F over 2. So what you get is QB F squared divided by 2. Alright, how do you find the moment about axis BB? Similar. It's Q times this length, A, times this length from here to here, times the moment arm. Okay? So that's how we find the design moment. Now you also have shear problems in footings. Okay, there's 2 different types of actions that can occur. The first is what's called one-way shear. This is like what we get in beams. The critical distance is at a distance of D from the column face. Okay, so if you take a look at that hashed line, the distance between AA and the shading is the distance D. Alright? Now, you have your uniform loading. Okay? You have your uniform loading below, right? What I'm saying is that the shaded area is the critical area for shear. So to find your demand, you multiply Q times this area in here. Alright? That would be the demand shear force. Now, how do you know what your capacity is? Well, it's the same as beams. The capacity is phi times the part from the steel plus the part from the concrete. Typically, we do not provide any stirrups inside of footings, so V sub S is equal to 0. However, the part from the concrete for one-way shear is 2 root FC prime, just like it was for beams. And when you multiply that by BD, that gives you a shear force resistance in the concrete. The demand, I told you again, was the uniform loading Q times this tributary area, or the shading part. You make sure that your capacity is greater than the demand, and you're okay. Your thing won't fail in shear.
Why did that tributary area kick out D all of a sudden? A minute ago it was jam up against the face. Now it's out.
Okay. For the previous part, it was for flexure. Okay? And if you flip your diagram upside down, where does your maximum moment occur?
Right at the face.
Okay, it occurs at the face of the column. Does everybody see that?
Yeah.
Now for shear, remember, shear forms by cracking at an angle of 45 degrees from the horizontal. So if I take a look here,
Okay.
the only way this guy can fail is like this.
Okay. I see.
So the reason we go out to a distance D corresponds to this point right here.
Gotcha.
Okay, so that would be our critical point. Now, there's also another problem that could happen. You could get what's called two-way shear, or punching failure. And this happens a lot in earthquakes, especially in slabs. What happens is that the column punches right through the footing. Okay? So you have a critical parameter here, and your crack is going to develop this way.
Critical perimeter?
Parameter, same thing.
Gotcha.
Okay, so what's happening is that this if I flip it over again, the uniform loading is making this footing slip down the column, and it slips along these cracks. This, from here to here now, what they say in the code is a distance of D over 2. Okay, for one-way shear was D, for two-way shear it's D over 2. So the tributary area for two-way shear is the shaded area, which is A times B minus this distance here, which is C plus D squared.
C being the column size.
C being the column width. That's correct. Alright. And again, same thing applies for two-way shear. Your capacity must exceed the demand. The demand is Q times this shaded area. The capacity is the part from the steel plus the part from the concrete. The part from the steel, again, in a footing, it's normally 0. So you drop that out.
Because you don't put stirrups.
No stirrups are used or required. All right. The part from the concrete, now you can use 3 different formulas. Because it's acting in a different direction, it's doing two-way action. It's failing all the way around and not along one length. You got to check all 3 of these conditions. The first one is that 2 plus 4 divided by beta times root FC prime BW, or B times D. Beta is the long side to short side of the footing. So if you have a square footing, beta is equal to 1. Okay? The other criteria, and this is wrong in your notes, it's alpha S times D divided by capital B0. Okay, not beta. Plus 2 times the root FC prime B times D. B0 is the critical shear length. So in other words, it's this dimension that goes all the way around the critical length. So in other words, if this length from here to here is CD, all the way around, it's just 4 times C plus D.
Is that alpha D over B, parentheses closed, and then you add a 2 to
and then you add a 2 to the result.
Okay.
That's correct. The third condition is that the resistance in the concrete is 4 root FC prime B times D. Okay, so you figure out which one's the smallest, you can go with that. You make sure that your capacity now exceeds the demand, and then it's okay for two-way shear. Alright. You also have to check... Yes? Okay, that's a good question. If you take a look on one-way shear, what's happening is that this footing, alright, if you take a look from the bottom here, the footing is actually sliding up the column, but only this part is sliding. Okay? Now, code criterion from a bunch of experimental tests, they found that the critical parameter was a distance of D from the column face. Alright? Now, for two-way shear, the mechanism is a little different. Alright, what's happening is that the whole footing now is sliding up the column. Alright, so in other words, if you flip it over again, okay, what's happening is that your whole footing is sliding through. So the column is punching right through. Now, that mechanism is different than the previous one. And from experimental data and all this stuff, they found that that distance now was no longer D, but D over 2.
And the way they show that on the pictures, too, is they'll kind of show this as not really coming out 45 degrees. They show it coming out kind of 45 and then like that.
Right.
And so that this distance right there was D over 2 instead of the full D.
Right, because you're getting... The phenomenon is that there's bending in 2 directions. Whereas in the first case, it was only into one because the whole part just sheared right off. But now we're getting shear that goes all the way around. So the mechanism's different. Alright, a lot of the stuff in the code in the concrete part, some of it don't make sense. And you say, well, where the hell does this number come from? But it comes basically from a lot of experimental tests. And, you know, same thing goes for development length. And I mean, where do you get these formulas from? It's just from matching experimental data. Okay. Capital B sum 0. Alright, and Lee, why don't you zoom in on this?
Okay.
Go more. You guys see that? Okay, it's called a critical shear length.
And show on the show.
I will. All right. Now, if you take a look at this near your column, that length is the distance from here all the way around. All right. That's what B0 is. So it's the perimeter of the cracked surface there. Okay, now there's other things you have to check. Number one is the concrete bearing stress. And this is the bearing stress on the column itself due to the axial load. The allowable stress is 0.85 FC prime times phi times the root of A2 divided by A1, where A2 is the area of the footing and A1 is the area of the column. This number must also be less than phi times 1.7 FC prime. Okay, so whichever one governs. There's also, you must make sure that the load gets into the footing. And the way you're going to do this is through dowels, which extend from the column into the footing itself. The area still required for the dowels must be greater than 0.005 times the gross area of the column. Standard practice is that you typically use 4 dowel bars. Okay? Generally, the number of dowel bars is equal to the number of bars that you have in the column. Okay, but not necessarily. Okay, you need at least 4 though. Now, as far as development goes, these bars that go from the column into, if I show you those bars in this previous drawing, dowel bars are going to go and dip into this footing. Okay? Now, how far it dips into this footing is based on the development length. Alright, so you have to make sure that this is enough development length, L sub D, okay, to make sure that those bars are fully active. Alright, so a quick procedure would be to select the footing size to satisfy the soil bearing capacity. So if you have an axial load on a column, you have to figure out, well, what size footing do I need? And remember, that bearing stress is going to be the axial force divided by the area of the footing itself. Okay? So you can select the size of your footing based on that requirement. Then what you need to do is to determine how deep this footing needs to be. That's this effective depth D. Then you're going to calculate the net factored earth pressure, and this is going to give us the uniform loading Q. And once we know Q, we can check for one-way shear. We find a critical area for shear for both one-way and two-way action, and make sure that the concrete has enough shear resistance so that we can avoid these failures. Okay? So if you do a check on one-way shear and you find out that the shear demand exceeds its capacity, you do not add shear reinforcement. What you would do is you'd make the footing deeper. And by making it deeper, you're going to increase its shear resistance. So you do the one-way check, you do the two-way check, and then you can design for bending. Alright, so figure out how many bars you need for bending, check the development length for these bars, make sure it fits, verify the column bearing capacity, and then design the dowels. Okay? Now, the next, yes? That's correct. Yeah, that's right. So your minimum criteria would be that your footing has to be at least 12 inches deep. That's true. Unless you use the hook on the end. If you hooked it on the end, then I think you can go down to 6 inches. You know, but in most buildings, I mean, the axial load that you got in these columns are very big. So you're talking footings that are maybe like 4 to 5 feet deep. Oh, wow. Okay, so that's basically the design procedure. Here's an example. Design a square two-way footing to carry live load of 240 kips, which is transmitted through a 16-inch square column. The soil allowable soil pressure is 4,000 psf, and the top of the footing is level with the surrounding soil surface. Use 3,000 psi concrete, 40,000 psi steel. Disregard column dead loading, but include the footing dead weight. So this is what we got. We got our column. we're going to make a footing that's square. This load is 240 kips. Okay? The soil on this side just comes up to the top part of the footing. So there's no soil sitting on the footing itself. Okay? Now, what we have to do is to assume, first of all, some footing thickness. You know, where does this number come from? Well, we know one thing. It has to be greater than 12 inches. Okay, so let's just say it's 20 for now. And when it's 20, D turns out to be, say, 16. Okay? Based on a 20-inch deep footing, well, what's the allowable net soil pressure then? Well, first of all, its capacity we know is 4,000. Part of that is going to be from the footing weight, and then the other part is going to be from the 240 kips. So let's figure out the net pressure. Well, if the allowable is 4,000, and we subtract off the part from the concrete, that's 150 pounds per cubic foot divided by times the thickness of the footing itself in feet. This says that the net pressure that we can put on this footing from the 240 kips is 3750 PSF. Alright? And if P is equal to 240, the required area turns out to be 64 square feet. So what we can select is an 8 foot by 8 foot square footing. Alright? And the actual pressure from this footing onto the soil turns out to be 3750. Alright, so everybody with me there? And I think these guys worked out perfectly just because of coincidence, all right? It's not that it works all the time. Now, the next step is to check one-way shear. Now, you already found your Q, all right? That's the 3750. Now, if we know the uniform soil pressure, right? We know that for one-way shear, the critical distance forms at a distance of D from the column face. Find for me this area in the shading. Well, it's just a rectangle. It's 8 feet times 12 gets me in inches times the width. Well, what's its width? It's 8 feet this way. Half of that is 4 feet, right? That brings me to the center of the column. We take half the size of the column, and in this problem it said that we have a 16-inch column, so that's 8, plus D. And D we already said was equal to 16 inches. So this critical area here turns out to be 16 square feet. Multiply this critical area times the 3750. This gives you a demand. All right, now the number turns out to be 102,000 pounds. All right, now where does the 1.7 come from?
Load factor.
1.7 is the load factor. You said to have some live load on there. So this is a load factor. Remember, we're checking for shear and bending, so this is ultimate strength design. We have to put that load factor on there. So it's 102,000 pounds. What's its capacity? Well, we already know it's phi times 2 root FC prime B times D. All right, now.
Now those are inches, 96 inches.
These are all inches.
Okay.
No, so we got 0.85 times 2 times root FC prime. B. What is B? B is the width that this shear crack is going to form. How does this form? It forms the whole width of the footing, doesn't it? So it's 8 feet times 12. It's 96 inches. Times D, the depth from the top of the concrete to the center of the rebar. And we know that's 16. The number turns out to be 143 pounds, or 143 kips, which exceeds the demand. Therefore, it's okay for one-way shear. It won't fail in one-way shear. Now, how do you check two-way? Again, same thing. You know the uniform loading. You got to find this area that's shaded. Well, what does that equal? It's the full area of the footing, which is 8 times 12, right? So that's one side, it's 96 squared, minus this inner part. Well, what's the inner part? I already told you. It's the column plus half a D on each side of the column. So it's the 16-inch column plus an additional 16 inches. That's 32. So it's a 32 by 32 inch square. So if you subtract that off, what you get is 56.9 feet squared. Okay? And what is this critical parameter now around the column here?
Perimeter.
Perimeter. I said parameter again. Perimeter. It's 4 times 32 divided by 12, which gets you into feet. So this turns out to be 10.67. So our demand is the 1.7 times the uniform loading, which is 3750, times the area, the critical area, which is 56.9. That's 362,000 and something. Okay? Now,
So let's say it doesn't fail in two, no, you haven't.
it doesn't,
have
this
you?
is its demand. Now we got to find the capacity.
Okay.
Beta is the long side, the short side, and since it's a square footing, it's equal to 1. Then there's 3 criteria for the concrete. It's 2 plus 4 over beta. Beta's 1. Root FC prime, B, D. So this is 673. The other one is alpha times D divided by B0. And again, this is wrong in your notes. B0 is the length of the perimeter of the crack. Alright, that's 10.67 times 12. That's what this number here should be. Instead of 1, it should be 10.67 times 12. So the final number over here turns out to be 785,000. The other criteria is 4 root FC prime BD. This number is 448. The bottom one's the one that governs. This is our nominal capacity.
Why does that one govern?
Because it's the smallest one.
Oh, okay, that's
The smallest one of the 3, that's the one that governs. This is our capacity.
That's the capacity.
Multiply by fee, this gives you 381,000 as compared to our demand, which is 362,000. So it won't fail in 2-way shear.
Sure came out close.
Comes out close.
How'd you get it so close?
I copy good out of the book. All right, now, for bending, we know it's not going to fail in 1-way or 2-way shear. So how do you find its demand moment? Now, I told you, these guys are just cantilevers, right? If you take a look at this, we have a uniform load underneath this footing. This part of the beam is just a cantilever. So the moment here at the critical face is 1/2 WL squared. So, there's your formula. W is the 3750 times your load factor times L squared. L squared is 3.33. The 8 is the width of the footing. Okay, to find the total moment, you divide by 8. This turns out to be 282,767 foot-pounds. Okay? Now, based on this moment, we go back to singly reinforced beam analysis, or beam design. Compute K. You know the moment, FC prime, B and D. B again is the 8 feet times 12, get you in inches. D is 16. You know all this, K turns out to be 0.0621. You have to make sure K is less than 75% of K balance. Here's K balance, is 0.436. The area steel required is the moment, divided by phi, divided by this. This number turns out to be 6.08 inches squared. Now that's the total area of steel that you need across the width of the footing.
This is all right out of that flow chart.
And this is all from the flow chart from the singly reinforced beam, right?
Okay.
Now, if you select 11 number 7 bars, that gives you an area of 6.6 inches squared. Or, this is the same thing as saying, let's use number 7 bars at 9-inch centers. Okay? If you divide the total number of bars by the width of the footing, what you'll find out is that you need to space these bars at 9 inches. Okay? And you'll notice the 9-inch centers is less than 3 times the thickness of the footing, and it's also less than 18 inches. So that's okay. Now we need to check development. This bar is used for bending. The bar here along the bottom. Is there sufficient development length from the face of the column to the end of the bar so that the bar becomes fully active at its critical moment? Well, you have to find the development length. That's that formula from the code. 0.04 AB is the area of the bar. For a number 7 bar, it's 0.6. FY is 40,000. FC prime is 3,000. This turns out to be 17.5, which is greater than 12. So this is the one that governs. Well, what do you have available? Well, the distance from the end to the face of the column, it's 4 feet to the center of the column, minus half of the column, which is 8 inches. This gives me 40.
And if it was less, you'd hook it on the end?
If it was less, you can provide a hook on the end. Right. All right. That's basically it for retaining walls. I can finish this up in about 5 more minutes. So can you hang for 5 more?
Oh, sure.
What a good bunch. All right.
You're thinking of your students. They'd be gone by now.
My students would be running. All right, retaining walls, I'm not going to get into it, but it's in Lindbergh. He has a nice flow chart there. It's on page 1433. So if you have a retaining wall problem, run to that section. Okay? I knew I'd be running out of time. That's why I did this. Another possible test problem could be in pre-stressed concrete. Okay? And for these, the whole first 2 sheets are basically allowable stresses for both the tendon, for the concrete, prior to transfer, after transfer, and long-term effects, etc. All right, I'm going to skip that sheet. I'm assuming that you can go check those numbers. The one I want to talk about is the analysis. The analysis of pre-stressed, simply supported beams with uniform loads. All right, the way this is done is that you first estimate the weight of the beam. Okay? And based on that weight, it's a uniform distribution. So the moment is 1/8 WL squared. Simply supported beam, uniform load, maximum load occurs at the middle, 1/8 WL squared. Now, assume the full beam in compression and calculate the neutral axis based on a transformed area. So what we're going to do is, because the dead loads are acting downward, we know the bottom part's going to go into tension. So what we want to try and do is put some tendons down here at the bottom and post-tension them, so that this part now doesn't go into tension. It stays in compression. Okay, so if we assume the whole thing is in compression, find for me the equivalent moment of inertia. Now, Dr. Lowry, I know, talked about this when you have to expand this area, right? Multiply that by n times a sub s and find the neutral axis, and then you can compute its moment of inertia. That's what I'm talking about here in step 4. Now, once you find the neutral axis, you can calculate how far the strands are from the neutral axis. That's this distance E. Okay? Now what about stresses? Alright, the stresses that are going to occur are 3 of them. Alright? Now, just imagine that you post-tension these rods. What are these rods going to do? It's going to try and squeeze the concrete beam together. Alright? And it's going to squeeze it together in a uniform distribution. You guys don't have this on your sheets. Alright? If you apply an axial compression force, what you're going to do is squeeze it together. So the stresses that you develop are P over A, compressive forces or stresses. And because the tendons are down here at the bottom, what it's going to do is it's going to create a bending moment about the neutral axis. If I take this beam and I post tension the bottom, what side of the beam is going to go into tension, the top or the bottom? If they're on the bottom, they're trying to pull in, the top part of it's going to try and push up, right? So you see here, if I draw compression stresses going to the left, okay? All my compression stresses go to the left. You see at the top, the tension stresses go to the right. So the top part goes into tension here, the bottom part goes into more compression. Well, what about the dead weight? Dead weight sits on the beam, right? And when it sits on the beam, the bottom side of it goes into tension. And you can see that from my third diagram here. The bottom part of the beam goes into tension. When you add 1, 2, 3 cases together, and you make sure that the bottom part and the top part, neither one of them go into tension, do you need any additional steel? No, because the concrete doesn't crack. That's the whole idea behind pre-stressed concrete, is that you can keep a concrete section from cracking its full length. That's why you can go to big spans on bridges and things, because when the concrete doesn't crack, it has a bigger stiffness, it can take more load with less deflection. Okay? Now, I'm going to put this up at the end of the lectures if you guys want to copy it, alright? So just hold on with that one.
Incidentally, Joe, we're going to ship a bunch of supplemental stuff, and you just stick it in that package if you want to. It'll go to them.
Okay, so I can send it that way also. I'll put it up after class, though. And I also included a sheet of all the pre-stressing tendons with their required areas. Again, you get a post-tension beam and they tell you to use a grade 277 wire strand, you have to have this table or you can't design it. Okay? The last part is masonry, and I'm going to ask a question. Has anyone ever designed masonry before? No. So skip this last section. I ain't even going to cover it. Don't do it. It's too hard. All right, and seriously, it's a review of masonry. It doesn't really do too much. If you guys haven't done it before, I recommend don't do it in an exam, so I'll save you some time and avoid covering that. But you got the notes if you want. So I'm going to put up that one sheet again with those stresses for pre-stressed concrete. And Dr. Lauer, if you'd hit that.
Well, I'm just going to mention something.
What are you doing there?
There's the guy that keeps us running, Chris. I tell you, without our chief technician here, we wouldn't have a prayer, so we appreciate his help.
Hey guys, I wish you a lot of luck. Sorry about killing you guys. I know it was bad.
Chris, anybody there got some questions? I think you're right. Okay, gents, we'll see you Wednesday night then, and we'll be starting on steel design. Pete Keating will be here for that.
Take it easy, guys. Good luck.
See ya.
Wait, these guys, a couple of them are still copied, so don't kill it yet.
No, we just usually let it run so everybody goes.
Well, they're not seeing anything, though. You would like them to see that?
There you go.
Move it around a little bit. Let's see.
Yeah, why don't you zoom that in?
And wide angle.
Oh, they can't see that.
Can't see that?
No way.
Okay, what do you want me to show them?
How's that, guys?
Until it settles down, they'll never see it anyway.
All right.
See, every time you move it, it goes smoky. And then it takes a little
You were
time
right
to settle
about, you were right
down.
about these sheets, because now I wrote all.
Yeah, but that's okay.
No,
That's why I was glad.
I got copies.
Sure, as long as you've got the original, you're okay. You just burn another copy on blue paper, and you got it made.
Good Lord, I didn't think I was going to make it.
It's quite a different thing, isn't it?
Your old voice started cracking.
3 hours. Yeah, I told you
it was
you needed
cracking.
another Coke.
It was cracking after an hour.
I told you needed another Coke. You wouldn't listen. You just gotta kind of